Hello people, today we're going to talk about the mathematical induction principle. So first let's see why it is important. For mathematicians, it's very important to save time, and induction is one of the things that help us to save a lot of time. Also because it is important because it is easy to do, we only need to verify two things to get the complete result, and also because it's very shared in many mathematical fields. So let's jump on it. First, I would like to begin with the intuition behind induction. I think that it is the most important part of mathematics. So you can't relate induction with dominoes, and the reason why is that we have a beginner on the induction and also a chain reaction. But it is important to formalize it a little bit, so that's what we are going to do in this short presentation. So, firstly, let's see some background knowledge that is important before the formalizations. Initially, we need to have clear which is the natural number set, which is this one, the ones that we used to count. Also, it's important to have clear what are direct proofs. Direct proofs are the ones related to prove if-then statements. We are going to see it in a moment. But the important thing here is to have clear what we have and also what we want. So let's see an example. They are called if-then statements because we have things between an if and a then. And what we have are the things that we can use along our proof, and then by our knowledge and also the hypothesis that we have, we can conclude what we want. So in our example, if we have that it is raining and also that we do not have an umbrella, we can conclude by our experience and also by this hypothesis that we have that we get wet, right? I know that it's very simple, but I think that is illustrative. So let's see about properties. Properties are it's at things that only implies n, and they are written in this way. So let's see an example. For any n in natural numbers, we have that 2 to the power n is less than 3 to the power n. The only thing that I would like you notice here is that n is only implied here. We do not have more variables here, and that's the thing about properties. So let's see the principle more formally right now. So the principle is at the end an if-then statement. So we need to verify what we have and also what we want. So what we have is the property over the natural numbers, and we also have two things: that the property is true for 0, and so that if it is true for n, it implies that it's true for n plus 1. So by having these two hypotheses, we can conclude that the property is true for all natural numbers that we have. Powerful, right? I know that it might be confusing the part of this thing, so we are going to see an example in a little, but I would like to give some names to the things that we have. When we have that property is true for 0, is what we are going to call the base step, and the difficult step is the inductive step. And in fact, the assumption that we have in this if-then statement is what we are going to call the induction hypothesis. So here is the formal principle for reference, and let's jump into the example. So we are going to prove that the sum from 0, 1, 2, until n is n times n plus 1 over 2. So initially, let's begin with the base step. So the base step is to verify the property for 0, and in fact it's only replace 0 in the formula. So on the left hand side, what we have 0, and on the right hand side, what we have, if we replace 0, we can add them, and also by multiplying it, we get 0 again. So since both sides are equal, we can conclude that the property is true for 0. We have a check here. So let's jump into the inductive step. Notice that there is also an if-then statement, right? So what we have, and the thing that we can use, is that property is true for n, and I wrote it here, and we have to conclude that the property is true for n plus 1. So our goal is going to be this thing that we have here, which is only to replace on this formula the n plus 1. So what we are going to do is to use this assumption to get the conclusion. So let's do it. First, we replace it by our induction hypothesis. We have this step. Then let's do a common denominator, which is simply to multiply by 2 on the numerator and denominator. And also let's add this thing. We have some like terms, so we can simplify. And here we have a factorization case. So let's try to work it. Initially, we take a square root of these two things and put into parentheses. And then we need to compute the signs. It's very important. So the sign that we had here, is doing by multiplying these two, plus times plus, we get plus, and also the sign that we have here is completed by these two, multiplying plus times plus. So we need now to find two numbers such that when we multiply them we get 2, and when we add them we get 3. The magic numbers are 1 and 2. So we have our goal. So let's see what we have. The induction principle asks us to verify for 0 and for n plus 1, and are the things that we already do. So by the induction principle, since we already do that, we had the properties valid for all the natural numbers, right? So I very welcome to questions and things that you didn't understand clearly.